Welcome to this video guide on heating and cooling curves. This session covers how substances change temperature and state, helping you understand the key concepts for your GCSE Physics exams. Today, we'll explore the science of heating and cooling curves, starting with their basic definitions. We will look at state changes, particle theory, essential practical skills for experiments, and top tips for your exams. First, let's understand heating and cooling curves. These graphs are essential tools for visualizing how substances react as they gain or lose energy. A heating curve plots temperature against time. You'll notice two types of sections: sloped sections, where the substance gains kinetic energy and warms up, and flat sections, which signify a change of state. A cooling curve is the mirror image of a heating curve. It illustrates temperature dropping over time as the substance releases energy to its surroundings, with flat sections marking where state changes occur. In summary, heating and cooling curves are opposites. Heating involves energy absorption, while cooling involves energy release. Importantly, both show the same critical temperatures for state changes. Next, let's dive into changes of state. We'll examine exactly what happens at melting and boiling points, and why temperature plateaus during these transitions. Matter transitions between solid, liquid, and gas phases at specific temperatures. Each state has unique particle behaviors: strong forces in solids, freer movement in liquids, and negligible forces in gases. At the melting point, a solid becomes a liquid. The temperature stays constant because the supplied energy is used to break the forces between particles, rather than increasing their speed. Similarly, at the boiling point, a liquid turns into a gas. The temperature remains constant again, as energy is utilized to overcome the remaining attractive forces, allowing particles to escape the liquid phase. It is a common exam question: why does the temperature stop rising during a phase change? The answer is that all energy is consumed by breaking interparticle bonds, not by increasing kinetic energy. When reading these graphs, remember that the first flat section is the melting point, and the second is the boiling point. The length of these sections indicates how much energy is required. Now we will look at particle theory and energy to understand why these curves take the shapes they do. During heating, energy is transferred to the particles, causing them to vibrate or move faster. This increase in kinetic energy is what we measure as a rise in temperature. Remember that temperature is a measure of average kinetic energy. In solids, energy is low. In liquids, it's moderate. And in gases, particles have high kinetic energy, resulting in higher temperatures. Energy is key to changing states. Instead of just increasing particle speed, energy is often used to overcome the intermolecular forces of attraction, holding particles in a rigid structure. During cooling, the process reverses. Particles lose kinetic energy to their surroundings, slow down, and move closer together, eventually transitioning from gas to liquid, and then to a solid. As a gas cools, it loses kinetic energy. At the boiling point, it condenses into a liquid, and at the melting point, the liquid freezes into a solid, with constant temperatures during these transitions. Moving on, let's discuss the practical side of this topic. How can you set up a controlled experiment to generate your own heating or cooling data? For accurate temperature measurements, ensure your thermometer is fully immersed in the substance, read at eye level, and is appropriate for the expected range and resolution. A controlled experiment is essential. Keep variables like your heat source power, time interval, and the total mass of the substance constant to ensure your data is valid. Recording at regular intervals is vital for capturing a clear curve. Consistent timing helps you detect the crucial flat sections that indicate phase changes without missing them. When plotting, label your axes with units, use small crosses to mark points, draw a smooth curve, and annotate the specific melting and boiling points observed. A typical heating curve shows rising temperatures during solid and liquid phases, with flat plateaus at the melting and boiling points where state changes happen. To boost reliability, always repeat your experiment at least 3 times. Calculating a mean average temperature for each interval minimizes the impact of random errors. Anomalous results are outliers that don't fit the expected trend. Identify them, circle them, and exclude them from your mean calculation to ensure your final graph is accurate. In the final section, we will review key exam tips and common pitfalls to ensure you avoid losing marks on your GCSE assessments. The most important tip: remember that a flat horizontal section on a heating curve always indicates a change of state. Master this, and you'll solve most questions. Avoid common mistakes. Don't claim temperature rises during a phase change. Don't confuse melting and boiling points, and never forget to label your graph axes with units. Finally, be precise with your language. Use terms like energy transferred rather than gets hot, and remember to draw smooth curves, not straight lines between data points. Let's review essential vocabulary. You must know these terms. Melting point is where solids turn to liquids, and boiling point is for liquids to gases. Remember, intermolecular forces are what hold particles together, and kinetic energy is related to the particle's motion and the substance's temperature. Beyond those basics, understand that a heating curve plots temperature against time while energy is added. A cooling curve shows energy loss. Both graphs highlight state changes, which are transitions between phases. Lastly, reliability is achieved by repeating readings to calculate a mean result. This visual recap shows the phases of a cooling curve. Notice that the flat sections occur at the exact same temperatures as on a heating curve. The boiling point and melting point remain constant regardless of the direction of the state change. Water is the classic example for GCSE questions. It melts at 0 degrees Celsius and boils at 100 degrees Celsius at standard atmospheric pressure. Recognizing these flat sections at these specific temperatures helps you quickly interpret what is happening in a graph. When describing a flat section, a full-mark answer explains that the substance is changing state and that the energy supplied is being used to overcome particle forces rather than increasing kinetic energy. Simply saying it is melting is not enough. Heating curves are used to identify unknown substances. You heat the substance, plot the results, and identify the melting and boiling points from the flat sections. You then compare these values against known data to determine what the substance is. Latent heat is the energy used during a change of state. The latent heat of fusion is required for melting or released during freezing, while the latent heat of vaporization is required for boiling or released during condensation. Vaporization typically requires more energy than fusion. To summarize, heating and cooling curves show temperature changes over time. Flat sections indicate energy is being used to overcome intermolecular forces during phase changes. Always prioritize consistent data collection and use clear scientific language in your explanations. Let's test your knowledge. What does a flat section represent? A change of state. Why does temperature stay constant? Energy is overcoming particle forces. How do you improve reliability? By repeating experiments and calculating a mean. You are now prepared to answer exam questions on heating and cooling curves. Remember the rules of state changes and particle theory. As a top tip, try sketching these curves from memory to ensure you have truly mastered this topic. Good luck with your studies.